At 3T, maybe you're talking about 2.5 or something like that. Still a big fold when you think, big factor when you think that you only gain that back as the square root of time. So, and also one thing we should, Jonathan, is pointing out that you have this nice amplification in cortex. Once you get below that cortical surface, bold is even less favorable. So if you're talking about subcortical activation, all of these should be increased by another 60%, maybe less than a factor of 2, but not something over that order, right? So there was one study a couple years ago by the Stanford group. I think Mosley was the last author. Greg Zaharchuk was on that. He came from our lab. They got about a CNR range. The data was not well presented, but at least it shows the main effects. They get like a factor of 2 to 3 at 3 Tesla. They explained that they had to fit this with a biphasic response, whereas the bold to fit with a single response. At this last ISMRM, another group, the NIH group, started doing this in people as well. And the stated goal of this response was to measure the impulse response function. So first they did localization using a block function, and so this is their data. Again, it's not flipped over, it's not normalized, it's hard to compare. So I drew these little lines on here, and you're seeing sort of the same sort of delay when they do the impulse response function. You see that the Fermat-Xatal response, again, has this long tail, whereas the bold is subtly undershooting. So at least the initial indications are we're seeing the same thing in people. But that's not the only, so there are other methods, right? So one method is this vascular space occupancy. And actually, I think it's an interesting method. The original hypothesis was perhaps flawed. So the original implementation is that you just do a single inversion. As it's going through the inversion, you image, and you have a 2-compartment model. You either have blood or it's not blood, right? And the not blood is tissue. And the hypothesis, as Peter Van Zyl described it, he said, well, everybody knows the way blood volume works is that as vessels expand, water just comes through, right? So it's not there's no displacement. And I thought that was very interesting. First of all, I thought that explains why we're seeing this slow component. And so I tried to do some calculations, and at least my calculations were, that process is at least several orders of magnitude too small. And I think people confuse water exchange, which is diffusion, which is on the order of a few seconds, with bulk displacement. Bulk displacement is described by the Starling equation. You've got to push water against these hydrostatic forces, which is not only the membrane, it's all the blood, all the water in your brain. That's a very slow process. And you know it's a slow process because if you ever have the misfortune to hit your head and get a little bleed, you're going to be building up more and more pressure in your brain to the point where eventually, if you not get help, you'll push your brainstem down into the spinal cord and you'll die. And you cannot extract water across the blood-brain barrier fast enough. People can give mannitol, and the osmolar difference will try to drive it out, but it doesn't work quickly. So this doesn't work. So the nice experimental.
I thought that half of the water leaves the capillaries, and the other the
But it comes back in. In other words, it's not a net displacement. So this is talking about a net displacement of water, a bulk displacement of volume, right? So a unidirectional extraction. This was nice work by Schouten and Constable, which seems to almost never get referenced, which they did a single inversion, and they showed with this breath hold, so it's a form of hypercapnia, that half the signal changes go up. If you calculate CVV, half of them go down, which is problematic. And so they said, well, the thing to do is the problem is that you're moving CSF around. So what you need to do is you do a blood nulling experiment, then you do a CSF null experiment. Then in those two you can combine and you can make sense of what's going on. And when they did that, this vasal B is vasal blood, vasal B and C is blood and CSF. When they combine those two, now you get a change in CVV with hypercapnia, which makes sense, right? So you have to take into account the fact that you're seeing signal changes because the blood vessels are expanding, but also that the CSF is shifting. And that gets back to this point that this is a cool technique, and I think it may have promise, but it's going to take some work because now you're talking about things which are not built upon a simple tracer. these are built upon T1 changes, or you might have other things which are built upon non-specific T2 changes, and then you have to dissociate the differences. So, when we did the contrast agent stuff, one of the things we noticed immediately is just a vast difference in how the maps look. Jonathan talked about the bold maps being weighted towards the cortex. The CVV maps are all weighted towards the center of the cortex. And largely that can be understood simply by the fact that you're specifically targeting tissue, a certain tissue blood volume fraction by the amount of contrast agent you choose. That means you're decreasing the amount of CVV, and it's just a contrast to noise argument. It's not really a physiology argument. So we wondered, does it really have a better point spread function? And I know we've been cautioned not to even use the word point spread function. So this has some limitations. One limitation is we're averaging through the cortical surface. This is monkeys. This is quite old. The other limitation is that we're using very discrete stimuli. So once you use very discrete stimuli, you're not going to see some of the vascular artifacts you use from extended stimuli. So basically, what we found is what everybody else has found, which is that our point spread function was a little bit bigger than our voxel size. Now, there was a paper by Huber et al. Using Vaso just very recently, where again they were describing the point spread function on the order of millimeters, right? But it's not millimeters. People who use 3 millimeter voxel sizes found 3 millimeter, impulse, shape, point spread functions. Here, so we tried to model this, and by far the biggest contribution is our voxel size.
I'm very confused.
Oh, sorry. So we're using retinotopy. So,
No. Just sampling theory. Okay. I mean, if your point spread function turns out to be the same size as the voxel size, it just says you're just limited by the sample.
well, exactly. You're limited by the SNR.
Yeah.
In the end.
Yeah.
Exactly. So we actually can, I think, pick up effects. The second biggest effect is T2 star blurring. And you start to use contrast agents, there's an advantage that you're nulling some of these big vessels, but there's a disadvantage that you're increasing the T2 star blurring. And at the end, we basically saw no real difference between bold signal and right? So although it's a parlor game in the MRI community to sort of bold bash, there's got to be something better than bold. There's CBF is better than bold, initial dip is better than bold. And I've been more than happy to join that game when it suits me. In the end, there's not a lot of difference, it seems like, fundamentally in what we're seeing. Now, that doesn't mean there aren't some advantages. This is from this Huber study. And what they're showing is that in areas where like, for instance, where if bold signal is weighted towards the cortical surface, you have a lesioncephalic species, that's not a huge problem. If you have a gyrocephalic species, sometimes you can't tell on which cortical bank your activation is because the two surfaces come together. And that's one thing that Wim van Duffel noticed when he first started using this method in monkeys, 15 years ago. He had a neuron paper. He said one of the big advantages is you can accurately localize the cortical surface. And so this is an example of Vaso, where by knowing the blood, you may at least be getting rid of the dominant blood weighted, but that doesn't necessarily mean that your signal is just a purely CVV weighted signal, and yet it may be useful, right? So it may have benefits to suppress. Okay, so this one I'm not going to speak about too much because, quite frankly, people here know much more than I do. But obviously, the fMRI, CBF is built upon these diffusible tracers. Going back to iota antipyrine, Rick has liked to use the microspheres, at least for PASL. There are various flavors. One thing which is just interesting to note is that ASL has been around as long as bold and was actually used in the first study. And people were actively investigating using ASL before Ken, at least in our laboratory, Ken stumbled onto bold, right? And it's amazing people didn't stumble onto that earlier because anyone can do it. And that's why I think people, in some sense, always looking for something which is harder because anybody can do it. But that's a little aside. But anyway, so this is just a simple example for those of you who aren't aware. This is a good pedagogical example because it shows arterial territory. If you just put it on one side, you magnetically invert the spins. They flow up. You do imaging, and you see the perfusion territory, and you get a nice clean subtraction on the opposite side. And You can do activation imaging, and basically, the takeaway is it works pretty well. It doesn't work as well as bold signal, but there are advantages. So here's just some random AXL examples. I'm not going to go through we could talk about the various trade-offs between like Passel and Castle and pCastle. But you can do imaging. We implemented just recently a pseudo-Castle, and here we're getting t-scores which are maybe a half to a third the size of bold, but they're reasonable. They're very well behaved temporal responses. But there are also advantages in situations where you absolutely want to use ASL. And there may be other alternatives, but this is an example. So first, it's a low task frequency. So let's suppose you want to image a drug, right? And you do, this is an example on the bottom where we were doing PET MRI. So we give a subject an antipsychotic, which has been repurposed as an antiemetic. And it's available as injectable form. It blocks D2 receptors. We measure PET occupancy. We're getting something like 75% occupancy. So the idea was we were going to look at how much dopamine was driven off of these and use that as an index of basal dopamine level, because the basal dopamine level and basal occupancy will scale, right? So this is going to be a method of measuring basal dopamine function. And we basically used a bold CSF sequence, bold ASL sequence, and couldn't see anything with bold. And that's not surprising, because we'd be looking for, a 1 or 0.5% signal change evolving slowly over tens of minutes, and it just gets lost in the drift. Now, one thing we didn't try, which would be a double echo, and that's something that possibly we could consider, but in a subcortical area like this, ASL probably is a good alternative, and here we are picking up a good response with ASL when we're not seeing anything with bold, right? So, and there's many other situations, like for instance, just evaluating what is the baseline perfusion in order to interpret your bold signal changes. All right, so let's move on to bold signal. So, oh no. So deoxygenated hemoglobin was known to be paramagnetic since the 1930s, right? And let's see if I can, maybe I have to do this again. Okay. So optical imaging in some sense got there before we did. It wasn't exactly clear what they're measuring, but there are very influential measurements by Grinwald and company where it was clear that they were measuring the oxygenation state. Ogawa started talking about bold signal based upon static images. So in our laboratory, Ken Kwong, sometimes we just say he stumbled upon this. Well, Ken was actually actively looking for ways to measure function non-invasively. So he was doing respiratory challenges in rabbits, for instance. And here's a picture of Ken with his famous goggles, which we have since displaced. We cannot locate these goggles. So he did photic stimulation on, off. He saw this. Everyone first thought, that's an interesting artifact, Ken. But it seemed to be in the right place. They made him go back and do it on a phantom and did not get the result. And so, at least in our laboratory, these were the first bold studies, and everyone's been doing it ever since. And so what is bold? So let's just use an accountant's version. This is very, very simple for those of you who don't know. So bold signal CBF brings oxygen in, drives bold signal up by washing deoxyhemoglobin out. CMRO2 does the opposite. It takes it out of the blood, depositing more deoxyhemoglobin. And CBV doesn't change blood oxygenation, but it puts more total deoxyhemoglobin into the voxel just by increasing the vessel size. And lastly, it's all modulated by how much deoxyhemoglobin was there to begin with. And this is this physics framework. It's been mentioned in David's study. The questions here, which is what are these couplings? That's one thing we'd like to do is both understand the coupling, but we'd also like to directly access CMRO2. So we come up with this measuring model. So really this started with with Tim Davis, but really, the start of Bruce Rosen. So it's actually in 1996 he was moderating a session, and he asked, I don't remember what it was about, but he asked the speaker, it was about hypercapnia, why, do you know if hypercapnia changes CMRO2? And I was, at that time I was a postdoc and didn't know a lot, but I was kind of confident, thought that was a strange question, said, why did you ask him that question? That was kind of unrelated. And he said, well, it just occurs to me that if CMRO2 doesn't change, if hypercapnia doesn't change CMRO2, we could use that as a calibration for something that does. And so Tim Davis, and he said basically, tasked Tim Davis and I to go on and do it, because in animal models we had the advantage of contrast agent, but in human models we had the advantage of humans. And really, it became a very simple method, whereby if you know something doesn't change CMRO2, and hopefully there's a series of assumptions here, but we're hoping that the CBF and CBV changes are representative of what's going on in the stimulus, right? And if that's all true, then all you have to do is account for the difference. So you have two unknowns, but if you take the CMRO2 out, you have one unknown, and then you get the bold effect. Sorry, the bold calibration constant. And with that, you can determine the CMRO2, right? So this is our data. We put it all together, and there's a disadvantage to this. The disadvantage is that these are, and this disadvantage will hold for like Vaso experiments, even if Vaso was accurate. Was that now you're putting together multiple sequential measurements, and you have to propagate error bars. I think you're never going to get reduction in error bars. You can investigate certain assumptions, but you're not going to get the reduction in error bars that you get in human studies. But we were getting, sort of 3 to 1, and there's been a whole series of studies, and they've all converged between, I guess 2 to 1 and 4 to 1 ratio of CMR2 to CBF. In human studies, you basically end up with this model, which is the model that was being shown by